students, welcome to this lecture. In this lecture we will continue our study of boundary value problems, and in this lecture and in coming lecture we will discuss the a special kind of boundary value problem known as Sturm-Liouville boundary value problems. But before that let us consider some preliminary for Sturm-Liouville boundary value problem. So first let us start discussing the concept known as adjoint equation. So exact equation is basically what we have already seen the exactness condition for first order linear ordinate first order differential equation, and in this case when you talk about first order differential equation, say y dash equal to f of xy, or you can say that when this kind of equation is written as d by dx of some g of xy, then we say that this equation which is now written in this form is known to be exact. Now let us extend this concept for second order and higher order linear differential equation. So the concept of exactness, which is usually discussed only for first order differential equation, can be generalized for higher order differential equation as well. So first of all we need to understand what exactness means. So the nth order differential equation given as like f of x, y, y dash and so on equal to 0 is said to be exact if the function f x, y, y dash up to yn is an exact derivative of some differential function of n minus 1th order, means just one less order, say g x y up to yn minus 1, or we can say that here your f of x y yn is written as d by dx of g of x y up to yn minus 1. And so in this case when this this equation this left hand side is now written as exact derivative of some differential function of one less order, we say that our differential equation is an exact differential equation. And in our lectures we will discuss only on second order. We can say that this is a general definition which is applicable for any order greater than or equal to 1, but in particular we will discuss only for second order in this lecture. So if we reformulate our definition for second order, we say the second order homogeneous linear differential equation Lu equal to p naught x p naught x u double dash x plus p1 x u dash x plus p2 x u x equal to 0, which is written as in operator form as L of u equal to 0. So in operator form it is written as L of u equal to 0 is said to be exact differential equation of second order if and only if for some ax and bx which is a differentiable function, we can write this differential equation p naught x u double dash plus p1 x u dash plus p2 x u as d by dx of ax u dash plus bx u. So we can, if we can write the term this p naught x u double dash plus p1 x u dash plus p2 x u dash px u as exact derivative of some differentiable form of one less order, that is first order, 2 minus 1 it is first order, and then we say that this equation Lu equal to 0 is an exact differential equation. So we can say that this Lu equal to 0 is exact if and only if we have this relation. How we get this relation? If you look at this, if you simplify this, this is what this you can write it here as a dash u dash plus a u double dash plus b dash u plus b u dash. So if you collect the coefficient, it is a u double dash plus u dash, and it is a dash plus b here plus b dash u, right. So it means that if we compare the coefficient here, so coefficient will be what? Coefficient of u double dash is a here, and here it is p naught x. So we can write p naught x is equal to ax, right. And if you look at the coefficient of u dash, it is p1 x here. So p1 x is equal to a dash plus b, and p2 x is equal to your b dash. So you here by comparing we can get the value of a and b, which we have written here, that ax equal to p naught and P1 is equal to A dash plus B, or we can simplify this to write that B is P1 minus P naught dash and P2 equal to B dash. So, using the value of Bx and B dash, we can say that the equation, this previous equation Lu equal to 0 is exact provided we have this P2 equal to B dash. Now, B is P1 minus P naught dash, P1 minus P naught dash. Now, P naught is what? P naught is A. So, we can say that equation is exact if this condition holds true. So, it means that this condition can be written as in simplification, if we simplify it is what? P naught double dash minus P1 dash and plus P2 equal to 0. So, it means that this Lu, which is now written as P naught u double dash plus P1 u dash plus P2 u is equal to 0 is exact if the coefficients of this differential equation satisfy this condition, and we call this condition as exactness condition. So, the differential equation 1 is exact if and only if its coefficient functions satisfy the following condition: P naught double dash minus P1 dash plus P2 equal to 0. And not only this, we can also write the equation P naught x u double dash plus P1 x u dash plus P2 x u equal to d by dx of, now A is this is P naught here. So, A u dash plus P1 minus P naught u. So, this is the value of B which we have calculated here. So, it means that I can write this as d by dx of P naught u dash plus P1 minus P naught dash u. So, it means that not only we are able to find out the exactness condition which is given by this, but we can also write the this differential form as derivative of this equation. Okay. So, it means that if this equation is not given in exact form, it means that the coefficient functions are not satisfying this relation, then we can find out any other function which makes this equation as an exact equation, and such a function is known as integrating factor. This is the same concept which we have discussed in first order differential equation. So, here we write an integrating factor for the differential equation Lu equal to 0 is a function Vx such that V into Lu equal to 0 is an exact differential equation. So, how we can find out this equation V of x, the function V of x. So, if you look at by multiplying by V, this must be exact differential equation. It means that Vx into this part must be some exact derivative of some differential form of one order less, that is d by dx of Ax u dash plus Bx u, and using this we can solving this we can find out the function V of x such that this VLu is an exact differential equation. And what is the use of this? Because we can use this because now your Lu equal to 0 is now reduced to this equation Ax u dash plus Bx u equal to constant. So, solution of this Lu equal to 0 is now reduced to solution of a differential equation of one order less, which is known as Ax u dash plus Bx u equal to constant, some C, some constant which we can determine later on. And in particular, if you look at the inhomogeneous differential equation Lu equal to Rx, then the solution of this inhomogeneous equation is given by the solution of Ax u dash plus Bx u integral of Vx Rx dx plus some constant. Now, this integral has a limit depending on the condition given along with this inhomogeneous linear differential equation. So, how to find out the integrating factor, which we will discuss a little bit later, but before that let us consider one example. So, consider the following differential equation x square y double dash plus xy dash minus y equal to 3x square. Basically, it is an inhomogeneous Cauchy-Euler kind of equation. and here without loss of generality let us assume that x is not 0, whether x is positive or x is less than 0. Now we can easily check that it is an exact differential equation, because the exactness condition is what? Exactness condition is p naught double dash minus p1 dash plus p2. Let us calculate this quantity. Now p naught is the coefficient of x double dash, that is x square. Find out the double derivative, that coming out to be x square double dash minus p1 dash is p1 is the coefficient of y dash, we write it like that, minus x dash, plus p2 is the coefficient of y, that is minus 1 here, and if you simplify this is what? This is simply 2 minus 1 minus 1, and it is coming out to be 0. So it means that this the differential equation LU equal to 0, it satisfies the exactness condition. So we say that this is an exact differential equation. So it means that now we can write it x square y double dash plus xy dash minus y as the derivative of this following quantity, that is p naught y dash plus p1 minus p naught dash y. So we can write x square y double dash plus xy dash minus y as x square y dash plus x minus 2x y whole dash. Now x minus 2x is nothing but minus of x. So we can say that this differential equation, inhomogeneous differential equation, x square y double dash plus xy dash minus y equal to 3x square is now written as x square y dash minus xy equal to x cube plus c. Here we are using this thing because this is what? This is written as 3x square. Now integrating both sides you will get this x square y dash minus xy equal to x cube plus c. Now we can say that this is a first order Cauchy-Euler's equation, and we can solve it quite easily, and we can solve it by saying that first solve the homogeneous problem, that is x square y dash minus xy equal to 0, and find out the general solution here. So once we have y general solution and a particular solution which we can check that it is x square in this case, so we can write the general solution as y of x equal to particular solution, that is x square plus solution of the homogeneous part, that is c1 by x plus c2x. So the general solution is given by this. Now we as we have already discussed that a function v belongs to C2 is an integrated factor for the differential equation 1 if and only if it is a solution of the second order differential equation p naught x v double dash minus p1 x v dash plus p2 x v equal to 0. How it comes, let us see like this. Here we already know that your LU equal to 0 is not exact. Without loss of generality, let us assume that this LU equal to 0 is not exact, because if it is exact then integrated factor is nothing but any function is an integrated factor, but let us assume that it is not exact differential equation. So here it means that p naught x u double dash plus p1 x u dash plus p2 x u is not exact. So it means that now we are finding a function v, so if we multiply this then it is an exact differential equation. So it means that now v p naught u double dash plus v p1 u dash plus v p2 u is equal to derivative of d by dx of some ax u dash plus bx u. Now we already know that this is an exact. If we have this relation, we simply say that coefficient of u double dash, that is v p naught double dash minus coefficient of u dash, that is v p1 dash plus coefficient of u, that is v p2 equal to 0. So we by the exactness condition we know that this happens only if we have this relation, that is v p naught double dash minus v p1 dash plus v p2 equal to 0. In fact we have just taken the coefficient of u double dash is this is now your p naught dash. I should not write p naught dash, let us use some other notation. We call it p naught tilde, and this is as p1 tilde and this as p2 tilde. So we already know that this is an exact provided that p naught tilde double derivative minus p1 tilde plus P2 tilde equal to 0. Now I am just writing the value of P0 tilde, P1 tilde and P2 tilde, and we have this relation. So it means that a function V is belonging to C2 category, C2 function is an integrating factor of the for the differential equation 1 if and only if it is a solution of the second order differential equation P0 x V double dash minus P1 x V dash plus P2 x V equal to 0. Now if you simplify this, we can get a relation like this. We can get this as P0 V dash plus P0 dash V one derivative minus P1 V dash minus P1 dash V plus P2 V. Now further simplifying, we have P0 V double dash plus P0 dash V dash plus P0 dash V dash plus P0 double dash V dash minus P1 V dash minus P1 dash V plus P2 V equal to 0. When we collect this, then we have this relation that P0 V double dash, that is here, plus 2 P0 dash minus P1 V dash. So we collect the coefficient of V dash. Coefficient of V dash is here, here, here and here. So it is 2 P0 dash minus P1 V dash plus the remaining part, that is we have here, here and here. So we can write it here. So by collecting this, we can get this term P0 double dash minus P1 dash plus P2 V equal to 0. So we say that the operator M in this 5 is called the adjoint of the linear operator L, the differential equation 5 expanded in to the differential equation this. So we simply expand this differential equation, which is given in this MV equal to 0. If we expand, we have this P0 V double dash plus 2 P0 dash minus P1 V dash plus P0 double dash minus P1 dash plus P2 V equal to 0, and we call this differential equation as the adjoint of the differential equation LU equal to 0, where LU is defined as P0 x U double dash plus P1 x U dash plus P2 x Ux equal to 0. So the adjoint of L is given as M, and we can easily check that if we find out the adjoint of M, then we can have some other equation. So now there is very important identity which is known as Lagrangian identity, which we can calculate from equation number 1 and 5, which is known as Lagrangian identity. So here from 1 and 5 we can say that V of LU minus U of MV. If we want to calculate this quantity, then we want to what we will get, that is known as Lagrangian identity. So let us first calculate this quantity. So VLU minus UMV. So when you write V, LU is basically what in previous slide which is already given LU. Now you just multiply V here minus UMV. So you multiply U here and just simplify, and you will get the following inequality, that is V P0 U double dash minus U P0 V double dash plus V P1 U dash plus U P1 V dash. So let us do it in here. So here your M of V is given as V P0 double dash minus V P1 dash plus V P2. So that is your MV, and if you calculate LU, LU is basically P0 double dash U minus plus P1 dash U dash, sorry, this is plus P2 U equal to 0. So here this is not dash, it is simply P0. Okay, so now let us calculate the now here we want to calculate this quantity VLU minus UMV. So let us VLU minus UMV, that we want to calculate. So VLU is what? V P0 double dash U plus P1 U dash V plus P2 UV minus UMV. So UMV, so UMV is V P0 double dash minus u v p1 dash minus u v p2. So this will cancel out here, what is left here is v p naught double dash u minus, let us write it here, u p naught v double dash plus p1 u dash v minus u v p1 dash. So now we want to simplify this, that is what it is written here, that v p naught u double dash minus u p naught v double dash plus v p1 u dash plus u p1 v dash, that is what it is written here. Now let us simplify this. I think there is some problem here, it is double derivative here. Okay, so when you simplify umv, I think there is a plus sign here, v p1 dash, here it is plus sign. Okay, so here we obtained this. Now let us look at this term here. So v p naught u double dash minus u p naught v double dash. So here we use this inequality w u double dash minus u w double dash. This can be written as w u dash minus u w dash whole dash. How we can write it? If you simplify this, it is what, w u double dash plus w dash u dash minus u w double dash minus u dash w dash. Now this will cancel out and we have w u double dash minus u w double dash, that is what is written here. So using this, and here this is simply u w dash is u w dash plus w u dash. This is simply product rule for derivative of functions. So using this, here your w is this, and so w is your v p naught. So using this I can write this term as we can simply write this as your v p naught u dash minus u v p naught dash whole dash plus, now this we write v p1 u dash. So using this, and if we simplify this, we can write it this as v lu minus umv as d by dx of p naught u dash v minus uv dash minus p naught dash minus p1 uv. So when you simplify, you will get this. So it means that this is written as what, you simply write d by dx of, and here you simplify like v p naught u dash minus u v p naught dash plus v p1 u dash. So using this you can write it this, that p naught dash minus p1 is uv. So here you have to simplify this. When you simplify this, you will get this. So v lu minus umv is equal to d by dx of p naught u dash v minus uv dash minus p naught dash minus p1 uv, and this identity is known as Lagrangian identity. So this is all, when you simplify this you will get this. And now let us consider this Lagrangian identity is very useful, and we will see that how this is useful in further lecture. So now we define one more important type of equation, which is known as self adjoint equation. So homogeneous linear differential equation that coincide with their adjoints are said to be self adjoint equation. It means that we have already discussed that corresponding to LU equal to 0, we have adjoint equation MV equal to 0, and if your operator L is ideally equal to M, then we say that our equations are given in self adjoint equation form. So it means that let us find out the condition under which equations are known as self adjoint equation. So necessary and sufficient condition for equation 1 to be self adjoint is that 2 p naught dash minus p1 is equal to p1. How we can identify this? So if you look at here, we have this L of u equal to 0. So this is what, this is p naught u double dash plus p1 u dash plus p2 u equal to 0, and we have obtained our MV equal to 0 provided that here we have V P naught double dash plus V P1 dash plus V P2 is equal to 0. There is small mistake here. The mistake is this, that this is your minus in place of so it is minus here. So if you simplify, we can write this as in this following format. This we have already calculated, that P naught V double dash. So we can write it here, P naught V double dash plus 2 P naught dash minus P1, 2 P naught dash minus P1 V plus P naught double dash minus P1 dash plus P2 minus P1 dash plus P2 V equal to 0. This is V dash here. So we say that LU is equal to simply MU, provided that the corresponding coefficients are same. So look at the corresponding coefficient. Here the corresponding coefficient of U double dash is P naught, here it is P naught, so no problem. If you look at the coefficient of U dash is P1 here, but here it is 2 P naught dash minus P1. So it means that 2 P naught dash minus P1 has to be equal to P1. So this is one set of condition which we know to. Now look at the coefficient of U here, this is your P2, and here it is P naught double dash minus P1 dash plus P2 here. Now if you simplify this, this is what? This you can get it 2 P naught dash is equal to 2 P1. So we can write it here, this as P naught dash equal to P1. So if you use this then P naught double dash is equal to P1 dash. So we can say that this condition also trivially satisfied by the next equation, that if you take P naught dash equal to P1, then this definition is automatically, this condition is automatically satisfied. So we say that your LU is same as MU, provided that we have P naught dash is equal to P1. That is what it is written here, that the necessary and sufficient condition for equation 1 to be self adjoint is the condition that 2 P naught dash minus P1 is equal to P1, or we can write it P naught dash minus P1. So it means that the coefficient of U double dash derivative is equal to the coefficient of U dash. That is what the condition is given here, and this proves the first statement of the following theorem. The following theorem says that the second order linear differential equation 1 is self adjoint if and only if it has the following form. So here if you look at our equation is reduced to what? P naught U double dash plus P1 U dash plus P2 U equal to 0. Now in place of P1 now I can write it P naught dash. So we can write P naught U double dash plus P naught dash U dash plus P2 U equal to 0. Now if you look at this, these two terms, then I can write this as d by dx of P naught U dash plus P2 U equal to 0. So it means that now I can write our differential equation in this following form, that d by dx of P naught x du by dx plus P2x U equal to 0. So if a differential equation is written in this particular form, then it automatically satisfies the necessary and sufficient condition for self adjointness. So it means that this kind of differential equation is known as self adjoint differential equation. And if it is not given in a self adjoint equation, then we can always find out the integrating factor by which we can make a differential equation in a self adjoint form, and we claim that the differential equation can be made self adjoint by multiplying thoroughly by this integrating factor, that is Hx equal to exponential of P1 by P naught dx divided by P naught. This is our claim. Let us prove this claim here. So to prove the second statement, we assume that our equation, that is P naught U double dash plus P1 U dash plus P2 U equal to 0 is not given in self adjoint form. So it means that your P naught dash is not equal to P1. So what we try to do here, we multiply by some function by which we say that it is your integrating factor. So before that multiplying, let us assume that P naught is never 0. So we can divide it by P naught. So when you divide by P naught, we write it as U double dash plus P1 divided by P naught U dash plus P2 by P naught u equal to 0. Now multiply by h. So when you multiply by h, you have h u double dash plus p h u dash plus q h u. Here ph is here p is p1 by p naught. So let us call this as p here and call this as q. So it means that we are writing u double dash plus p u dash plus q of u equal to 0, then multiply by h. So we have h u double dash plus p h u dash plus q h u equal to 0, where p is p1 by p naught and q is p2 here. Now our claim is that here this is an exact differential equation. So it means that this is a given in self adjoint form. So it means that if it is self adjoint form, then derivative of this u double dash must be equal to the coefficient of u dash. So it means that h dash must be equal to p of h. So this equation is in self adjoint form if we have h dash equal to p of h, and this is a first order homogeneous differential equation. So we can easily solve this equation to find out the value of h, and if you solve, then equation of h is given an exponential of p dx, where p is this p1 by p naught. So it means that the equation 8 can be made self adjoint. So it means that if we multiply here by h by p naught, then this equation is in the form of self adjoint form, because this h we are multiplying in this kind of equation. But if we have p naught, so first we have to divide by p naught and then multiply by h. So it means that our function h, which we need to multiply to make this equation as self adjoint form, is the following function hx equal to exponential of p1 by p naught dx divided by p naught. So if we multiply this equation, then our equation is reduced in a self adjoint form. Let me look at here. So h is coming out to be what? H is coming out to be exponential of p1 by p naught x dx. So now h we are multiplying here in this equation. So it means that if we multiply h by p naught into this equation, that is p naught u double dash plus p1 u dash plus p2 u, then this is what? This is h u double dash plus here we can write h p1 by p naught u dash plus h p2 by p naught u equal to 0. So if your h is this, then this can be written as d by dx of, now here this you can write it exponential of p1 by p naught and u dash plus this h p2 by p naught u equal to 0. So if you look at making this as a self adjoint, the only rule is of the coefficient of u dash and coefficient of u double dash. So we need not to worry about the coefficient of u at all. So now we say that self adjoint equation is very common, and it is written in this particular form: d by dx of p naught x du by dx plus p2x u equal to 0. And if it is not given in self adjoint form, then we can always multiply by function this, which we have denoted as the equation number 9. We can make a linear differential equation into a self adjoint form, and so it means that now onward, without loss of generality, we can always consider that a given second order linear differential equation is given in self adjoint form. And here we note one thing, that in this case for self adjoint differential equation, the Lagrangian identity is now simplified, and it is given as VLU minus ULV equal to d by dx of p naught x u dash v minus uv dash. In fact, it is d by dx of p naught and Wronskian of uv. So that is what, why? Because in self adjoint form your p naught dash is equal to p1, and if you look at go to Lagrangian identity, then Lagrangian identity the coefficient of uv is p naught dash minus p1. So self adjoint form, in self adjoint form your p naught dash is equal to p1. So this will cancel out in the case of self adjoint equation forms. So what remains is d by dx of p naught u dash v minus uv dash. That is what it is written here, d by dx of p naught x into Wronskian of uv. So, here Lagrange identity simplifies to VLU minus ULV equal to d by dx of p naught x u dash v minus uv dash, and which I can write it as minus of d by dx of p naught x w of uv. So, now let us consider one example. So, consider the Chebyshev differential equation. So, here we want to reduce the following differential equation to self adjoint form. Right now it is not given in self adjoint form, because if you differentiate this 1 minus x square, it is given as minus 2 of x, which is not the coefficient of u dash. Coefficient of u dash is only x. So, it is right now this differential equation is not given in self adjoint form. So, let us make it self adjoint form. So, here we just compare from the differential equation, and we say that p naught is equal to 1 minus x square, p1 is equal to minus x, and p2x is equal to lambda here. So, we already know that the factor by which we can make this equation as a self adjoint equation, we can calculate hx as exponential of p1 by p naught dx divided by p naught. So, p1 is minus x and p naught is 1 minus x square. So, we can calculate this hx as 1 upon 1 minus x square, this is p naught, into e to power 1 by 2 minus 2x upon 1 minus x square. This we can simplify, this is what this I can written as 1 upon 1 minus x square exponential of 1 by 2, and this is ln of 1 minus x square. So, we can write it this as 1 upon 1 minus x square, and this is what under root of 1 minus x square, and we can simplify and we can have hx as 1 upon 1 minus x square power half. So, it means that by multiplying this function hx, we can make our differential equation as self adjoint differential equation. So, multiply throughout by 1 under root 1 minus x square, we have this following differential equation: 1 minus x square half u double dash minus x divided by under root 1 minus x square u dash plus lambda this. You can easily check that here the derivative of this is given by this. So, this is given in self adjoint form. Now, let us look at one more example. So, that if u and v are solution of the self adjoint differential equation, then this quantity p u dash whole dash plus q x u, this is the self adjoint equation given here, then p x into u v dash minus v u dash is a constant. So, this is the self adjoint equation given in this way, and we say that u and v are solution of this, then the following quantity is a constant quantity, and this is a straightforward example, because since the given equation is self adjoint form, then we have v l u minus u l v is equal to d by dx of p x of v u dash minus u v dash. So, we already know that u v are solution of this. So, l u is equal to 0 and l v equal to 0. So, this part is going to be 0. So, it means that p x v u dash minus u v dash is equal to 0, right, and this says that the given p x v u dash minus u v dash is a constant value, right. So, this example is a straightforward example based on Lagrange identity. By using Lagrange identity for self adjoint form, we can easily say that this quantity d by dx of p x v u dash minus u v dash is equal to 0, and by integrating we can say that p x v u dash minus u v dash is equal to a constant value. So, here we end our discussion, and in next lecture we will start with the Sturm Liouville boundary value problem. That is all for this lecture. Thank you very much for listening. Thank you.